Hello friends, welcome to UGC EPG Pathshala. I am Swati Katyar, Senior Research Fellow, Birla Institute of Scientific Research, Jaipur. Today in this episode, we will discuss about the LIDAR basic principle and applications. We will start with the introduction. LIDAR is an acronym for light detection and ranging. It provides very accurate high resolution 3D data captured using special sensors from the air or the ground. It results in a set of dots suspended in a three-dimensional space. These dots can be displayed in a special software or converted into a 3D mesh for use in many modern 3D software packages such as a 3D Studio Max, Maya and SketchUp. LIDAR technology uses light sensor to measure the distance between the sensor and the target object as shown in the figure number 1. From an aircraft, this includes objects such as ground buildings and vegetation. For ground-based LIDAR, it measures building fronts and street furniture in extreme detail. With the latest technologies, it is also possible to obtain color values of the scanned surface to create automatically textured model. LIDAR is ideal when high accuracy measurements are required and is very cost effective for the amount of data generated. Airborne LIDAR is becoming more and more popular as a source of terrain mapping due to the high level of detail it provides, as shown in the figure number 1. Now we will discuss the brief history of the LIDAR. The oldest known variation of a modern LIDAR system evolved in nature millions of years ago. Christopher, most commonly known as the BAT, uses echolocation guidance system now known as a sonar. They emit short chirps from their noses and receive an echo through their ears in the form of two antennas. This provides the bat with a three-dimensional view of the surrounding area, allowing them to avoid obstacles and easily find their prey. LIDAR sensor works on the same principle as that of the radar, firing a wavelength at an object and timing the delay in its return to the source to measure the distance between the 2 points. Because laser light has a much shorter wavelength, it is possible to accurately measure much smaller objects such as aerosols and cloud particulates, which makes it especially suitable for airborne terrain mapping. LIDAR has been used extensively for atmospheric research and meteorology due to the excellent resolution. It was only with the deployment of GPS in 1980s allowing the precise positioning of aircraft that made airborne LIDAR surveying possible. Since then, many downward-looking radar instruments have been developed for aircraft and satellite use. Now we will discuss how does the LIDAR works. The basic principle behind LIDAR is quite very simple. Shine a small light at a surface and measure the time it takes to return to its source. When you shine a torch on a surface, what are actually seeing is the light being reflected and returning to your retina. Light travels at very fast speed, about 300,000 miles per second or 0.3 meters per nanosecond. So, turning a light on appears to be instantaneous. The equipment required to measure this needs to capture extremely fast. Only with the advancement in the modern computing technology has this become possible. The actual calculation for measuring how far a returning light photons has traveled to and from an object is quite simpler. As given in the below equation, the LIDAR instrument fires rapid pulses of laser light at a surface, some up to the 150,000 pulses per second. A sensor on the instrument measures the amount of time it takes for each pulse to bounce back. Light moves at a constant and known speed, so LIDAR instrument can calculate the distance between itself and the target with high accuracy. By repeating this in a quick succession, the instrument builds a complete map of surfaces it is measuring. With the airborne LIDAR, other data must be collected to ensure accuracy. As the sensor is moving at a height, location and orientation of the instrument must be included to determine the position of the laser pulse at the time of sending and the time of returning. This extra information is crucial to the data's integrity. With the ground-based LIDAR, a single GPS location can be added for each location wherein the instrument is set up. Generally, there are two types of LIDAR detection method. The very first is the direct energy detection, also known as incoherent and coherent detection. Coherent systems are best for Doppler or phase sensitive measurements and generally use optical heterodyne detection. This allows them to operate at a much lower power but has the expenses of more complex transceiver requirement. Unlike the coherent radar, incoherent LIDAR does not require laser wavefront coherence from the sensor through the turbulent atmosphere and back to the sensor. Incoherent LIDAR successfully look through the temperature and humidity gradients and turbulent environments wherein coherent system may fall. In both type of LIDAR, there are two main pulses module, micropulse and high energy systems. Micropulse system have development as a result of more powerful computer with a greater computational capabilities. These lasers are lower powered and are clear and are classed as eye safe, allowing them to be used with little safety precautions. High energy systems are more commonly used for atmospheric research, where they are more often used for measuring a variety of atmospheric parameters such as the height, layering and density of clouds, cloud particulate properties, temperature, pressure, wind humidity and trace gas concentration. The very first one is lasers. Lasers are categorized by their wavelength. 600 to 1000 nanometer laser are most commonly used for non-scientific purposes, but as they can be focused and easily absorbed by the eye, the maximum power has to be limited to make them eye safe. Lasers with a wavelength of 1550 nanometer are common alternative as they are not focused by the eye and are eye safe at much higher power levels. These wavelengths are used for longer range and lower accuracy purposes. Another advantage of 1550 nanometer wavelength is that they do not show under the night vision goggles and are therefore very well suited for military application. The second component is scanners and optics. The speed at which images can be developed is affected by the speed at which it can scan into the systems. A variety of scanning methods are available for different purposes such as azimuth and elevation, dual oscillating plane, mirrors, dual axis scanners and polynomial mirrors and polygonal mirrors. The type of optic determines the resolution and range that can be detected by a system. The next component is photodetector and receiver electronics. The photodetector is the device that reads and records the signal being returned to the system. There are two main types of photodetector technologies: solid state detectors such as silicon avalanche photodiodes and photomultipliers. The next component is navigation and positioning systems. When the LIDAR sensor is mounted on a mobile platform such as satellites, airplane or automobiles, it is necessary to determine the absolute position and the orientation of a sensor to return usable data. Global positioning system provide accurate geographical information regarding the position of the sensor, and the inertial measurement unit, that is called IMU, records the precise orientation of the sensor and that location. These two devices provide the method of translating sensor data. The next is LIDAR laser and scanning system. The LIDAR instrument consists of a system controller and a transmitter and a receiver. As the aircraft move focused along the lines of the flight, a scanning mirror pulses of laser light across track perpendicular to the line of flight, as shown in the figure 3a. Most LIDAR used far topographic mapping uses eye-safe infrared laser light in the regions from 1040 to 1060 nanometer. Blue-green lasers centered at approximately 532 nanometers are used for bathymetric mapping due to their water penetration capability. LIDAR data can be collected at night if necessary because it is an active system not designed on solar illumination. LIDAR system can emit pulses at rates greater than 100,000 pulses per second, often referred to as a pulses repetition frequency. A pulses of a laser light traveling at c, that is the speed of light. LIDAR technology is based on the accurate measurement of the laser pulse travel time from the transmitter to target and back to receiver. The travelling time of the pulse of light t is given in the below equation, where r equals to the range between LIDAR sensor and the object. The range r can be determined by rearranging the above equation as follows. The range measurement process results in a collection of elevation data points arrangement systematically in a time across the flight line as shown in the figure 3b. The range measurement process results in a collection of elevation data points referred as mass points arranged systematically in a time across the flight line as shown in the figure 3b. The example displays mass point associated with the ground, several power lines, a pole and a tree canopy as shown in the figure 3a. Now we will discuss about the types of LIDAR. Airborne LIDAR. Most airborne LIDAR systems are made up of the LIDAR sensor, a GPS receiver and IMU unit, onboard computer and a data storage devices. The LIDAR system pulses a laser beam point onto a mirror and projects it downward from its airborne platform, usually a fixed wing aeroplane or a helicopter as shown in the figure 4. The beam is scanned from a side to side as the aircraft flies over the survey area, measuring between 20,000 to 150,000 points per second. When the laser beam hits an object, it is reflected back to the mirror. The time interval between the pulse leaving the airborne platform and return to the LIDAR sensor is measured. Following the LIDAR mission, the data is post-processed and the LIDAR time interval measurements from the pulses being sent to the return pulse being received and converted to a distance and corrected to the aircraft's onboard GPS receiver, IMU and a ground-based GPS station. The GPS accurately determines the aircraft position in terms of latitude, longitude and altitude, which are also known as the x, y and z coordinates. The LIDAR sensor collects a huge amount of data and a single survey can easily generate the billions of points totaling several terabytes. As IMU is used to determine the altitude of the aircraft as the sensor is taking measurements. These are recorded in degrees to an extremely high accuracy in all these dimensions as roll, pitch and yaw, the vertical horizontal movement of the aircraft in a flight. From these two datasets, the laser beam exit geometry is calculated relative to the Earth's surface coordinate to a very high accuracy. The initial LIDAR data can be further enhanced using additional post-processing, some of which can be automated and some of manual. Further processing utilization the multiple return signal from each laser guide. By evaluating the time difference between the multiple return signals, the post-processing system can differentiate between buildings and other structures, vegetation and the ground surfaces. The process is used to remove surface features to produce the Earth models DTM. It is also possible to do selective feature extraction, for example, the removal of trees and other vegetation to leave just the buildings, as shown in the figure number 4. Now we will discuss about the ground-based LIDAR. Ground-based LIDAR systems are very similar, only that an IMU is not required as the LIDAR is usually mounted on tripod, which the LIDAR sensor rotates 360 degrees around. The pulse laser beam is reflected from objects such as building fronts, lamp posts, vegetation, cars and even people. They return pulses as recorded and the distance between the sensor and the object is calculated. The data produced is in a point cloud format, which is a three-dimensional array of points, each having x, y and z position relative to chosen coordinate system. The structure of the ground-based LIDAR is shown in figure number 5 below. Now we will discuss about the application of LIDAR. The first application is the forest planning and measurement. LIDAR is widely used in the forest industry to plan and manage, as shown in the figure number 6. It is used to measure vertical structure of the forest canopy and also used to measure and understand canopy bulk density and canopy based height. Other uses of the LIDAR in the forest industry are the measurement of the peak height to estimate the root expansion, Riano identified using LIDAR the height of the tree cover height and canopy cover, crown base height and the crown bulk density. First generated a digital terrain model by differentiation of laser pulses with lower height and laser interpolated using the spline function. Thus, the vegetation height was estimated by removing the ground elevation above sea level. Depending on the individual pulse's height by an algorithm based on a cluster analysis, differed the variables tree height, crown base height and the shrub height, and the classified the pulses differentiating the trees, shrubs and the ground. Crown bulk density was obtained by dividing crown foliage biomass over the crown volume. The crown biomass was modeled using empirical specific equations for the estimation, and crown volume was calculated directly volume between trees height and canopy base height. Now, second application lies in the region of forest fire management. LIDAR becoming widely popular in the forest fire management. While fire department is transforming from reactive to proactive fire management, LIDAR image helps to monitor the possible fire areas, which is called the fuel mapping. In the fire management, DTMs can be used as a topographic inputs or as a base elevation maps, which can be subtracted from canopy and vegetation heights to assess fuels. Topographic information such as slope, elevation, aspect can be used as a direct input into decision support systems such as FastSight, which is fire area simulator, and Behave, which is fire behavior prediction and fuel modeling system. These inputs are essential to successful fire behavior prediction modeling, as shown in the figure number 7. Digital terrain models also provide the base elevation, which is subtracted from the digital surface models to estimate the vegetation height and a fuel. LIDAR derived DTMs can be extremely detailed with the absolute positional accuracies below 15 cm in the vertical dimension and 50 cm in the horizontal dimension. Now, the next application lies in the river survey. Water penetration green light 532 nanometers of the LIDAR is used to measure underwater information. Underwater information is required to understand the depth, the flow strength, width of the river and more. For the river engineering, the cross section detail is extracted from the LIDAR data to create a river model, which will create flood and flood fringe map. In the same way, to understand the underworld, LIDAR data is used by the marine engineer, as shown in the figure 8. LIDAR provides very accurate information. River is very sensitive and a very few meter change can bring disaster or loss of properties. So, LIDAR is used to create high resolution and accurate surface model of the river. These extracted LIDAR information can be used for the 3D simulating for better planning of the structure or building onto the river bank. Now, the next application lies in the management of the coastline. LIDAR data of the coastline surface and underwater surface can be combined by the researchers to analyze the waves behavior and area covered by them. If these data are captured periodically, then marine scientists can understand the coastline erosion's occurrence. The next application is in transport planning. LIDAR data for a road helps engineer to understand it and given a road map for the building, as shown in the figure number 9. As a LIDAR are highly accurate technology, it helps to understand width, elevation and length of the existing road. Road engineer uses LIDAR data for below things as well as calculate cut fill, culvert sizing, vegetation removal, grade calculation and more height clearances, right of way and surface conditions. LIDAR technology uses near infrared band of the electromagnetic spectrum and measures the time it for a laser pulse to travel from the transmitter to the target and back to the receiver. Because the light speed is known, the distance can be calculated. An accurate timing system is needed to guarantee the resolution. because the laser pulses are sent at a 3000 to 10,000 times or more per second. The aircraft positioning is powerful using an inertial navigation and associated with the avionics system and high accuracy global positioning systems and GPS base station installed to known locations. Thus, it is possible to determine 3D georeferenced coordinate for each plane and then correct the aircraft positioning in terms of roll pitch and heading, thereby improve the system's accuracy. Modern LIDAR system can operate at a laser pulse repetition frequency of 50 to 100 kHz per second. The density of the ground points depends on the aircraft elevation, the number of pulses per times the scanner angle and the aircraft speed. To cover the dense areas, multiple lights can be combined for high resolution topographic data. A LIDAR mission is flown at a low altitude. After the field data collection process is completed, the data points already in the digital format are easily loaded in a computer. Stations for processing and integration. Airborne LIDAR technology presents several advantages compared with the traditional methods such as photogrammetry and the total station ground survey. The data collection using the field survey can produce accurate information. However, this method demands a team to measure distances, and photogrammetry uses a stereoscopic analysis of an aerial photograph to generate a digital elevation model in the post-processing, which can also be time consuming. Using LIDAR, time consumption can be reduced considerably because of the high data collection speed up to the 81 square kilometer or the 20,000 acres per day, and the data are collected and stored digitally. The next application lies in oil and gas exploration. As LIDAR wavelengths are shorter, it can be used to detect molecules content in the atmosphere that has same bigger wavelength. There is a new technology called DIAL, that is differential absorption LIDAR, which is used to trace amount of gases above the hydrocarbon region. On the southern bank of the Sangmo Arc that has a recent oil development wells and mostly situated in age with some Devonian production. A LIDAR survey was flown between December 2014 to March 2015 by digital aerial solution using a Leica ALS70. Slope angles map using ArcGIS 10.3 were created from an terrain data. 12 divisions were used with quantile classification and green to red color ramp. Green is the lower slope and red is the higher slope. Quantile places are equal amount of data in each division and results in a good signature of the higher slope angles in relatively low slope areas. Natural breaks or junks classification is more appropriate for the areas of high slope. Now, the next application lies in archaeology. LIDAR has played an important part for archaeologists to understand the surface, as a LIDAR can detect microtopography that is hidden by vegetation, which helps archaeologists to understand the surface, as shown in the figure 11. DEM created from the LIDAR is fed into GIS system and it is combined with the other layer for analysis and interpretation. From 2012 to 2015, archaeologist Damonian and Evans with his team used LIDAR technology mounted on a helicopters to map some 2,230 square kilometer with an accuracy of plus minus 150 millimeters. With the 16 data points measured every square meter, the researchers were not only able to pinpoint well-known monumental stone structure in exquisite detail, they also discovered the massive urban culture which surrounded these temples, identified by the remain of the earthworks such as. The next application is solar energy planning. Solar energy are getting popular for heating and electricity purposes. Solar panels are used to absorb the heat energy from the sun and it is converted to heat or electrical energy. For the installation of the solar panel, there are some basic requirements which are identified by the help of the LIDAR data. Like the solar panel should be kept to south facing of the roof and it should have a minimum area and so on. The next application lies in glacier volume changes. LIDAR is used to calculate the glacier change over the period. LIDAR images are taken in time earlier to see the change happening. For example, LIDAR images was taken in Iceland from 2007 to 2009 and project was completed by 2012. These captured data will help scientists to know the amount of volume change. The least square 3D surface matching method is put forward by the Ermin Gruen for the problem statement of surface patch matching and its solution method in photogrammetry in 1985. Gauss-Markov model, the proposed method estimates the 7 transformation parameters among different surfaces and minimizes the sum of squares and the Euclidean distances. It has been widely used among terrain changes monitoring, commercial measurements and photogrammetry. Based on this method, Miller also successes in acquiring glacier volume changes results in a Stockholm district in Norway using the ESTER data and LIDAR data. Using light detection and ranging, data collected from the surveys covered 6 glaciers in Greenland and Antarctica. Particle image velocimetry was applied to temporarily spaced point cloud to detect and measure surface motion. The type and distribution of the surface features, surface roughness and the spatial and temporal resolution of the data were all found to be important factors which limited the use of PIV to 4 of the original 6 glaciers. The PIV results were found to be good agreement with the other widely accepted measurement techniques including manual tracking and GPS and offered a comprehensive distribution of velocity data points across glacier surface. For 3 glaciers in Taylor Valley, Antarctica, averages velocities range from 0.8 to 0.1 meter per year. For 1 glacier in Greenland, the average velocity was 22.1 meter per day. Now, LIDAR application in gaming. LIDAR technology is used to capture the surrounding area and this data is fed into the computer and color code is added to it. For example, for the racetrack game, LIDAR will be used to capture the view of the real racetrack. This captured racetrack data will be used for the game. Now, LIDAR application in recording of building. Ground-based LIDAR can be used to record the inside of the houses. It can be used to record the interior design too. This extracted data can be printed on the 3D printer to model it, or when the building is rebuilt, this recorded information can be used to restore the interior design. LIDAR application in mining. LIDAR is also used in the mining business in various tasks. It is used to measure the volume by taking series of photos of ore extraction space. These interval photos are used to calculation the volumes. Internal surveying. LIDAR is used to measure accurate and detailed measurements used for analysis, measurements and modeling of the tunnel, that is far railway track or a road. This might be in the mountain, land or underwater. Hope you have enjoyed the lecture. Thank you.